And today we will discuss something like technical things. I tried to make it more entertaining for you and more, let's say, meaningful. Just not only the formulas, but some illustration of these concepts. Why do we need this topic, which is called large sample asymptotics? Is just to justify some tools that we will be using in the next topics. So this is basically the let's say the fundamentals or some common grounds of the subsequent techniques that we will be using. So yesterday we introduced a statistic which is called a sample mean. We said that this is a random variable, and this random variable is just a combination of random draws of this same random variable, and we have n of them. So yes, we said that this is a random because it is a function of independently identically distributed random variables from x1 to xn. Yesterday we introduced some characteristics of this sample mean distribution. Namely, we said that the expectation or expected value or the center of the distribution of this sample mean is located exactly at the mean or expected value of each of these variables. And the variance of sample mean is just sigma squared over n over the sample size. Well, sigma squared is the variance of each of these variables. So all these variables are identically distributed, and therefore each of these variables has the same variance, which is sigma squared. But we may come with different examples of distributions that have the same mean and have the same variance, but the shape of the distribution is different. So that's why still there is a question: what is the form of a sample mean distribution? So yesterday we concluded the lecture with the example of three tosses of a die and the calculation of a sample mean, and we were able to establish the probability distribution of a sample mean. We just needed to calculate all 216 possible outcomes and then to calculate how many of them lead to the particular value of the sample mean. Yeah, so in order to derive this explicitly, we need to know the distribution of this variable. But back to the yesterday lecture, we introduced that the problem of statistics is such that usually in practice we don't know the distribution of this random variable. I don't know what is the distribution of an age or salary of people living in any country, in Russia, in China, in the United States, wherever. So I don't know what is the distribution of this random variable. I don't know what is the distribution of the tomorrow stock price of Google or Amazon or Gazprom. I don't know this distribution, and nobody knows, because those random variables are not the product of our mind. Those are just the products of some real processes. So the question is there any other way to infer the distribution of a sample mean? Look, I'm talking about the distribution of a sample mean without knowing the distribution for this particular random variable xi. And we will answer this question today. So that's why I'm saying that today's lecture is more or less technical, because we need to prove that there is, under certain circumstances, under certain conditions, there is a distribution of a sample mean that we can use as an approximation even though we don't have the exact distribution of the individual random variable. So let's look at some illustrations. So today I decided to produce some illustrations for you just to see, to understand the concepts of what's going on. So imagine the following experiment. We have a random variable from one of the following three distributions. So I just took three distributions and I produced the random samples from them. So one distribution is binomial with 100 repetitions and the probability of success 0.1. So let's say this is something like, well, so the binomial random variable will say how many times, let's say, if I test 100 people for COVID, how many people will show the positive result. If the probability of testing positive for one person is 0.1. So the expected value is 10 for this variable. Exponential with lambda 0.1. So the expected value is also 10 for the exponential distribution. So the exponential distribution, if you remember, this is something about time or probably the losses if we look at the application of finance. And the uniform distribution of the interval from 5 to 15. Again, so the expected value of this random variable is going to be 10. So the center of this interval. So we have three different random variables. Now, the experiment is the following. Yeah, so in all three cases, the population mean is known and it equals 10. So now we do the following. I take a sample of one observation only and calculate the sample average, which is just degenerate, right? So I take x1 and so the realization and divide it by 1. Then I draw a sample of a size 2. So I take 2 observations from each of these 3 distributions and I calculate the average of their realizations. I take a sample of 3 and calculate the sample average once again. And I proceed and I keep doing this again and again and again for a larger and larger and larger sample. So you remember yesterday we did the same for 4 dice, right? So we just took 3 dice, we toss them, and then based on the outcome we calculate what is the realization of a sample mean. I did it in Excel. So be careful, I'm calculating the average of realizations. So I have exact numbers. So what I want to see? I want to see if there is some particular behavior of this sample average, realization of the sample average, if the sample size increases. Is the idea clear? Once again, I have distributions. I generate some outcomes from these distributions, so some numbers like 10, 15, 5, 1, whatever. They're really random, so I did them with the help of Python, so then I will demonstrate you how it works if you want. And I change the size of my sample. So first time I draw only 1 number, then 2 numbers, then 3 numbers, then 4 values, 5 values, 6 values, 7 values, and so on. And then I calculate their average. So what happens? Let's see. So here is a binomial distribution. Look, on the horizontal axis, I have the sample size from 0 to 10,000 observations. So 10,000 numbers. And on the vertical axis, I have the exact value of this sample average. So the value starts if the sample size is small, like 1, 2, 3, whatever. So the value deviates too much from its true value because the true expected value is 10. You remember this. But then what happens? when the sample size increases, my actual realizations become more concentrated around this sample mean. And the concentration so becomes tighter and tighter. This distribution becomes tighter when I move towards infinity. So when the sample size increases. So this is something like a convergence. I increase the sample size, I increase n, and my realizations become very, very close to the true expected value, to 10. So what happens with the other distribution? Oops. So here is an exponential distribution. Again, for a small sample size, I have huge variation, but then immediately when the sample size increases, my realizations become tightly concentrated around the true population mean, true expected value. So what happens in the third case, in the uniform distribution? The same. Same thing happens when I increase the sample size, the averages of my random draws become tightly concentrated around the true population mean. So what does this mean? It means that no matter what is the underlying distribution of my random variable, whenever I have large enough sample, the average of the values that I can calculate, the simple arithmetic average, will point with a very high probability, will point towards the true population mean. Of course, there is some uncertainty. Look, because it never becomes the flat line. It never becomes a flat line. It never becomes exactly equal to the true population mean. But it becomes very, very small. The deviation becomes very small and it becomes very close to the true population mean. And you see that as I increase the sample size, this deviation decreases. So I can find in principle the such sample size that will produce the given value of an error that I want to achieve. So this is the illustration of something which is called the convergence and probability. So this is a really important concept that helps us a lot to overcome the problem of unknown distributions of a random variable. So the formal definition of this convergence and probability says the following. If we have a sequence of random variables, this xn, this is exactly what I have here. And then I have some variable x, which is known for me from the previous course of probability. So this is just some conceptual random variable defined on some sample space. So then, what is the definition of a convergence in probability? So we say that this random variable xn, or this sequence of random variables, converges in probability to this variable x if I take any arbitrary epsilon, which is greater than 0. So just some positive constant. I take some number. And then probability that the deviation of my random variable xn from this variable x, so the deviation, I take this as an absolute value, so I don't care whether it's positive deviation or negative deviation, just deviation. And the probability that this deviation is going to be greater than or equal to the taken constant is gonna in limit when n goes to infinity. So the limit of this probability will be 0. So in words, it means the following. As I increase the sample size, this sequence goes to some variable x, and my random variable, as I increase the sample size, so deviates from this variable x by a very, very small amount, and the probability of this is going to be 0, that it will be greater than this very small amount. Or vice versa. So the probability that this deviation is going to be less than the desired value epsilon is going to be 1. Or let's say goes to 1, tends to 1. I know that usually this limit language is kind of difficult to understand, so then I will illustrate you once again this concept of convergence and probability, so don't panic about this. So I hope you will understand. So this is going to be the notation in this case. So we will write that the sequence of random variables xn converges in probability to x. That's a shorthand notation. And we will call this variable x the probability limit, or plim of this sequence. Be careful. So what we had on the previous slide is not exactly what we have here. Because, look, because here we had the particular realization of a sample for each sample size. So only one realization for each sample size. Here we have a little bit different thing. So look, the meaning is the following. So assume that I want to take a sample size of, let's say, 1000. And I want to calculate the sample average. What is the probability that this sample average will deviate from the true population mean by some amount, let's say by 1 or by 2, by 3. And if the probability that it will deviate from this value, if the probability that the deviation is going to be greater than this value is 0, so then I say that this sample mean with this size of 1000 converges to this to the true population mean. So let me illustrate to you this idea once again. So let's take some particular distribution, binomial, with 100 draws and the probability of a success 0.1. Let's take 3 arbitrary constants epsilon, 5, then 1, then 0.5. So I'm making this deviation smaller and smaller and smaller. Like here, I will take 5, then 1, then 0.5. Okay, so that's what would be the next thing. Then I will take several sample sizes from 1 to 10,000. So this n, so I think 10,000 is huge enough to consider this as going to infinity. So I will be changing this n. Then I need to know what is the probability that the sample mean will deviate from the true population mean. So the true population mean here is 10. So how to know this probability? We have some formal ways to do this. Basically, with the help of probability theory, I could have derived this in the formal way, but I don't want to do this. I want to show you the following. So I will make 1000 random samples, and in each sample I will find the sample mean, and then I will calculate the deviation of this sample mean realization from 10, and out of 1000 random samples for each sample size, I will calculate how many times this difference exceeds epsilon. And this will give me something like a probability that under the sample size of 1, this difference exceeds, or let's say the sample mean exceeds 10. With the sample size 2, this difference exceeds minus 10 exceeds 5, and so on. Then I make it smaller. I make epsilon equal to 1 and do the same. Then I make it smaller once again and do the same. Basically, I will find something like not the strict, not the probability in a strict way, but this is gonna be some like proportion. And if this proportion goes to 0, so the fraction of times when this difference exceeds epsilon, then the sample mean converges to 10. So look what happens. If I set epsilon to 5, so here on the horizontal axis I have the sample size, and here I have the fraction or the ratio or the proportion of times when under the sample size, let's say 1 or 2 or 3 or 4 or 5, the actual realization exceeds, doesn't exceed 5, sorry, here is less than or equal to. And you see that this fraction tends to 1. Basically, it starts from 0.88, or a bit less, and then it goes to 1 immediately. When the sample size gets larger, the probability that this actual average will deviate from 10 by 5 units becomes negligible. So when I make this difference tighter, when I want to have the deviation of a sample mean from the true population mean no more than 1, again, so the probability that this will deviate by more than 1 will very fast, very soon become 0, and the probability that this difference between the sample average and 10 will be within this interval of 1 becomes very close to 1. And when I make this even tighter, so again, this probability becomes 1 around the sample size of 6,000, maybe less. Is the idea clear? What happens here? Once again, I could have shown this with the help of formulas that, well, the probability that the sample average will not exceed, sample average minus 10 will not exceed 5, and then we will see that this probability goes to 1 when n increases. This is the formal way of showing it. Well, basically, I don't think that we need to know such deep technical things. So you're bored enough with the probability things from the probability course. So now I'm gonna show you more like simulational things. Is the idea clear? What is the convergence? What is the convergence in probability? So basically, when you take a large sample, the probability that your random variable will differ from the target, from that x, in our case, the probability that the sample average will deviate from the population mean by some amount becomes 0. the probability that will not deviate by this given amount becomes 1. This is the convergence in probability. So there are some properties. We would need them in the next lecture to justify some useful tools when we make the analysis of the data. So if we have two variables, two sequences of random variables, xn and yn, and these two sequences converge to the corresponding to the respective variables x and y, then their sum converges in probability to the sum of these probability limits, to the probability limit of xn and to the probability limit of yn, x and y respectively. If you have a random variable, if you have a sequence, of random variables that converges to a random variable x in probability, and we have some constant, then when we multiply this sequence by this constant, the probability limit might be also multiplied by this constant. This is something natural. In many different fields we have these similar properties. If the sequence converges to some constant a, and then we have some function g which is continuous at a, then the function of the sequence converges to the function of this constant. So for example, if we have a sample mean and the sample mean converges to the population mean, then the sample mean squared will converge to the population mean squared, which gives us a chance to prove that all the sample moments, second, third, fourth moment, converge in probability to the population moments. But we will discuss this later. So if we have two variables, something similar to the first property, convergent in probability to their respective probability limits, then the product of these sequences converge in probability to the product of these random variables. Again, we will need this. So I will refer to these properties in the next lectures. And finally, we have one very nice result from this concept of convergence and probability. So this result is called weak law of large numbers. So usually people use this law of large numbers concept in many different and wrong ways. So the law of large numbers says precisely the following. If you have a sequence of IID random variables, so IID is really important here, and all these IID random variables have the common mean mu and variance sigma squared, and this variance must be finite. This is another important concept. And we have a sample mean xn, then this sample mean converges in probability to the population mean. That's what we have seen in the previous slides. So look, I don't put any particular assumption on the distribution of xi. I don't care what is the distribution of xi, whether it's binomial, exponential, Bernoulli, whatever. I just care about this. So basically all the distributions that we have covered by this moment, they have the finite second moment. They have the finite variable, Poisson, hypergeometric, whatever. There are some special distributions that have infinite variance. So for example, Cauchy distribution. But we are not talking about this Cauchy distribution in this course. So if you would ever need this, so just remember that there are some distributions without this property. And you see that this convergence in probability works for all of the for any distribution, and we have seen it here. We see that the actual realizations of the sample average tend to be very close to the population mean when the sample size increases. That's exactly the illustration of this weak law of large number. Which means the following: whenever you have a task to calculate or to infer about the true population mean of some random variable, what is the true population mean of stock return, what is the true population mean of the car accident losses, what is the true population mean of the corporate profitability, what is the true population mean of the salary of working people, whatever. You are recommended to have large enough sample in order to be at least somehow sure that what you will calculate converges in probability to your target, to what you are looking for. Samples like 5 or 10 people are not usually enough to infer something about the population, even if they are random. But samples large enough, like 10,000 people, maybe 100,000 people, are okay. But also you must be careful, because the sample size must be still small relative to the population size. Don't forget about this. So there is a balance between how large must be the sample size. From on the one hand, it must be large enough in order to at least be to some extent sure that the weak law of large number works. On the other hand, this sample size must not be so huge that it covers half of the population. So this is one story, and this is one thing that would help us in particular. So any questions about the convergence and probability, law of large numbers, and the practical implications of this? Once again, so the practical implication that you must usually work with the huge enough sample, not with, do not consider or do not make some inferences about the populations when you have an experience about like 3, 4, or 5 observations. That's usually, the fallacy of people when the person gets some real life experience, like 1, 2, 3 times, and then the person decides that everything is constructed in the same way. So law of large numbers doesn't work in this way. If you have an experience and if you observe really huge sample, and this sample is random, must be IID, then probably you can talk something about things in general. Okay, so now another important thing. So the second concept in this lecture that we need to cover, which is called the central limit theorem. So once again, I want to show you some intuitive illustration. So we know that the sample mean under the condition of a large sample converges to the true population mean in probability. So now, still, the exact value of the sample mean depends on the random sample drawn, right? So you see that there is no flat line of the sample mean. There is some deviation of the sample mean from the true population mean. And for example, going back here, for example, what if the true, so what can I say about the true population mean if I have something like this? So the true population mean might be not 10, but for example 10.002 or 10.05, something like this. It also might be true, right? Because I don't know where exactly my sample mean converges. Okay, in this case I know that there is a 10, but in principle, if I don't know the distribution of my random variable, I don't know where exactly my sample mean converges. So therefore, there is still some distribution of the sample mean, even though I increase the sample large enough. And well, I still want to know what is the distribution of the sample mean. That's the first question we posed in this lecture. Let's make another experiment. Let's take the same three distributions, binomial, exponential, and uniform. But now the experiment will be a little bit different. I will take, let's say, three random sample sizes, 10, 100, and 1000. Okay, so 1000 might be good enough. And then for each size of a random sample, I will do the following. I repeat the calculation of a mean, of a sample mean, 10,000 times. I will draw 10,000 random samples. And for each sample, I will calculate the sample average. And then I will build a distribution of those sample averages. So what would be this distribution? So once again, like when I showed you the convergence to the true population mean, I took only one random sample for each sample size. Now I take three sample sizes, 10, 100, 1000, and I do 10,000 draws of random sample for each size. So I draw 10 numbers from a binomial distribution and calculate their average. I draw another 10 numbers from the binomial distribution and calculate their average. I draw 10 numbers in the third time, 10 numbers in the fourth time, and so on, and I repeat doing this 10,000 times. And then I'm getting different averages. And I'm calculating the distribution. I want to build the distribution of those averages. That's something similar to what we had yesterday with the 3 dice. I throw 3 dice once, calculate the average, throw 3 dice. Second time, calculate the average, and so on. So in this case, I do this for the sample 10, for the sample 100, for the sample 1000. So let's see. So here is a binomial distribution. If the sample size is 10 and the distribution of sample averages looks like this. There are some blank spaces, okay, but still looks familiar. Moreover, the variance. Look, the variance of the sample mean is huge. So the sample mean varies around 10, but it varies from, let's say, 8 to 12 or even more. So now, when I increase the sample size, when I take the sample of 100 observations and then I calculate 10,000 averages, 10,000 times. Okay, so the shape is more or less similar, has some values here, and the variance becomes smaller. So this distribution becomes tighter because now the maximum and minimum are around 9 and 11. Still it's centered around 10. So here, for the sample size of 1000, it's still centered around 10, and the variance becomes even smaller. So remember the result from the last lecture. The variance, where is that? The variance of a sample mean decreases with the increase of a sample size. You see that this is sigma over n. So when I increase the sample size, the variance decreases. That's what we see here in these graphs. Look, the variance for the sample size of 10 is kind of huge. Here the variance decreases, and here the variance decreases significantly because now the sample mean varies from something like 9.6 to 10.4. What the shape of the distribution looks like, does this remind you something from the probability course? Let's look, this is something like the probability density function. Empirical, it's not the theoretical one. It's built on the real observations, but still. Does this look familiar? Which distribution has similar density function or graph of probability? Okay, think about this. We will move to the exponential distribution. So let's see what happens with the distribution of a sample mean once we draw random samples from the exponential distribution. So look, here it looks skewed. Who remember whether it's right skewed or left skewed? Do you remember about your feet? I was talking about this. So
This
how
is right,
to...
right.
This is right skewed, yeah. So we see that basically, so it tends, the tail is skewed to the right. Yeah. Okay, when the sample size increases, so the skewness somehow disappears. It goes here, here it becomes symmetric. Once again, the variance decreases because the variance here is huge. It's from 0 to 20. I mean, not the variance, but the range, right? So the range of values is from 0 to 20. It's very huge. When I increase the sample size, the range is from, I don't know, 6 to 14. And now it's from 9 to 11. So the same thing happens as before, as here. Why? Once again, remember, because the variance of a sample mean decreases with the sample size. It's sigma over n. So in principle, if n is 10,000, the variance is going to be very small, but still positive. The third, uniform distribution. Well, for the uniform, we have this situation with almost no tails in the distribution. When the sample size increases, the variance decreases first, and then we have these tails, and here, almost perfect tails. Still symmetric. So, has anybody remembered how do we call the distribution of this shape? Come on, guys. Where was it? Lecture 7. Oh, 8. It's here. Looks like a normal distribution. The bell shape, probability density function. So that's here, right? So once again, doesn't matter which distribution we have, binomial, exponential, uniform. So all three, the sample means for all three, with the increase in the sample size, somehow move towards the normal distribution. And this is very important and striking result, because as we started from, if I don't know what is the distribution of my underlying random variable, but I have large enough sample, I know, or at least I can approximate the distribution of a sample mean with the help of a normal distribution. Here, here, and here. For three particular distributions, we see almost the same result, which is brilliant, I guess. So now we don't care what is the underlying distribution of the random variable. We know that the sample mean would tend in the distribution towards the normal distribution. So this introduces us to another important mode of convergence, which is called the convergence in distribution. So be careful, those are two different concepts. So convergence in probability means that the probability that your random variable would deviate from some constant or some other random variable becomes negligible, and convergence distribution means something a bit different, because now the start is the same. So we have a sequence of random variables, xn, and we have some random variable x, which is defined on the sample space. So just, I don't know, any random variable. And then we have CDFs, cumulative distribution functions of this sequence and of this random variable. And of course, we want this to be continuous. So this is going to be the set C of f of x. This is going to be the set of points of continuity of this random variable. This is just technical thing. Well, for our course, we will not consider the situations when there is not continuous distribution. So now, we introduce the concept of convergence in distribution, which means the following. So the limit of the cumulative distribution function of this sequence as n goes to infinity equals to the cumulative distribution function of this random variable x for all points, for all values of x, for all realizations that belong to the set of where this CDF is continuous. That's something that we have seen on the three previous slides. So something that we have seen there. So the distribution of a sample mean with the increase in the sample size converges to the normal distribution. So we will denote this as with the following notation. So xn converges in distribution to x. And we will refer to the f of x and x as the asymptotic distribution, large sample distribution, or limit distribution of xn. So that's where these asymptotics come. That is in the name of the lecture. So the large sample asymptotics means that when you have a large sample, so the distribution asymptotically converges to some known distribution of this x. Let me illustrate you this with the help of exponential distribution. Why? Because exponential distribution on the previous slides showed some degree of skewness. So the sample mean of the exponential distribution. So that's why I decided to take this one. So let's say we have a random variable xi. This is exponentially distributed. Lambda is 0.1. So therefore mean is 10 and variance is 100. I take three sample sizes, 1, 5, and 15, just to illustrate you the idea. So we can take any of them. So 1, it means that I'm taking one value from the exponential distribution. 5 means that I am taking 5 random values of the exponential distribution. 15 means that I am taking 15 random values, some realizations from the exponential distribution. Then I do the following. For each sample size, as for the probability for the convergence probability, I draw 10,000 random samples. And then I calculate the sample mean for each sample draw. And I build the following. So I build the, let's say it's called empirical CDF, but in principle, it's gonna show me how many times, what is the fraction of samples when the sample mean is less than or equal to some particular value, small x. And then I compare this with the CDF of a normally distributed variable x with mean 10, same here, and variance 10 over n. Remember that the sample mean is distributed with this variance, it's sigma squared over n, which is, in the first case, it's going to be 100. In the second case, it's going to be 100 over 5, which is 20. And in the third case, it's going to be 100 over 15, which is 20 over 3, right? So let's see what happens. So here is, so the blue line is the CDF of a sample mean when the sample size is 1, and the orange line is the theoretical CDF, cumulative distribution function, of a normal distribution with M10 and variance 100. So then I increase the sample size to 5. You see that the blue line becomes much closer to the orange line, but not enough. Then I increase the sample size to 15, and the blue line becomes almost matching the orange line. So we can take in principle the larger sample size, like 20, 25, 50, 100. So let's try. So the code is still available here. Let's take the sample size of 100, let's say. Let's see what happens. It will take some time to calculate. We see that these two lines are almost identical now. So this is the idea of convergence and distribution. So the distribution function of your random variable, of this sequence of random variables, becomes closer to the theoretical distribution function. In our case, this theoretical distribution function is the normal one with n, with the mean 10 and variance of this 100 over n. So practically, it gives us the following result. Whenever your sample size is large, you can believe that the sample mean is distributed normally. Well, as for the properties of convergence and probability, we introduce some properties of convergence in distribution. So when a variable converges in probability to something, then it also converges in distribution to something. But the converse is not true in general. So if something converges in distribution, it doesn't mean that this converges to the probability. Converges in probability, the same variable. Once we have one variable x, or one sequence xn convergent in distribution to x, and another sequence yn convergent in probability to 0, then there are some converges in distribution to x. This is something natural. If y converges to 0, then of course the other term converges in distribution to x. If I have a variable that converges in distribution to another variable, and I have some function g, which is a continuous function on the support of x, then the function of this sequence converges in distribution to the function of this random variable. This is similar to the convergence and probability and their functions. And this is called Slutsky theorem. So the same Slutsky as you heard from the microeconomics. So he also worked in probability. So if you have several random variables, xn, x, an, and bn, and we have two constants, a and b, and if xn converges in distribution to x, and an converges in probability to some constant, and bn also converges in probability to some constant, then the linear combination converges in distribution to a plus bx. So all of these properties are going to be needed in the subsequent material. So we will prove with the help of them how the statistics calculated from the data are distributed under the large sample properties. And you will also do some exercises on the exercise session with the help of this, so that just to illustrate how this works. So now the final thing in this lecture, the final result in this lecture, which is based on the idea of convergence and distribution, and we call this a central limit theorem. Let's say we have the observations of a random sample, x1, x2, xn, so random variables. They are IID. They have the distribution with the mean mu and positive variance sigma squared. Non-zero variance must be. Then the following construction. Well, this is more familiar, I hope, to you. So x minus mu over sigma, but now sigma divided by the square root of n. So what's that? Let me remind you from the same lecture as we had here. Look, we had a random variable z in this form, x minus mu over sigma. I hope you remember, and if you don't remember, then please review this lecture once again. Then this variable has something which is called a standard normal distribution. This variable has mean 0 and variance 1. Look, now we are talking not about x, which is distributed normally with mu and sigma squared. Now we are talking about some variable x bar n. So this is the sample mean. And we know that the sample mean has the same population mean, mu, but the variance of a sample mean is not sigma squared. It's sigma squared over n. Therefore, in the denominator, instead of sigma, I must have sigma over square root of n here, this thing. That's where this comes from, this square root of n. Because whenever I want to normalize this value, look, it's not x, it's x bar. Here, compare this. So the variance of this x bar is sigma squared over n. Therefore, when I take the square root, it's going to be sigma over square root of n. And this is just multiplied by n. Whenever I multiply this ratio by n, I will have the sum of xi here minus n mu here, and the square root of n instead of denominator becomes in the numerator here. Okay, so these two fractions are identical, but this fraction might be more familiar to you. And please remember this fraction. We will be using this fraction almost every day from now on. So this thing has the converges in distribution to some variable z, and z is the random variable that has a standard normal distribution. So now we are done, because now we know what is the distribution of a sample mean. Now we know that under the large sample property, the sample mean, or at least the transformation of this sample mean with the following way, has a standard normal distribution. Perfect. Congratulations. We know a very important thing. Now, to conclude what we have done in this lecture. So, in large samples, sample mean, convergence probability to the true population mean of x of the variable of interest. In large samples, this fraction converges in distribution to the standard normal distribution, 0 and 1, which now gives us a chance to calculate some probabilities that the actual realization of the sample mean under some special sample, because usually we work with only one sample. What is the probability that this deviates from the true population mean by some amount? So this gives us a powerful tool for working with the random samples and making inferences about the unknown distributions of the random variables of interest. Because now, with the help of these two things, we can make a lot of interesting conclusions, even if we don't know something about the underlying random variable. Yesterday, we posed a problem. Today, we partially solved this, because now we showed that we don't need to know what is the underlying distribution of the random variable of interest. Once we have a sample, once we calculate the sample mean, with the help of sample mean, we can do a lot of interesting things. And yesterday, we introduced the idea of statistic. So what is statistic? This is the function calculated based on the random sample. Sample mean is not the only statistic. Yesterday we introduced another statistic, which is sample variance. We have much more statistics, of course, since the name of the course suggests. In econometrics we will have even more statistics. And of course, not all of them are distributed normally in large samples. So that's why we need to know more about sampling distributions, which are based on this normal distribution. We will talk about this in the next lecture on Thursday. We will introduce new sample distributions for different statistics, how to deal with them. So that's all regarding today's material. Now the home assignment comes. So first of all, yesterday I asked you to install Anaconda. So you still have a weekend to do this. I guess it's not that difficult for you. And please don't miss the last thing here that considers the installation of necessary libraries, because basically this Jupyter notebook, which is used to code in Python, it works like, let's say, some toolbox. Whenever you need to work with some special functions and special tools, you need to take a special library of these tools. And well, that's why you need to install these libraries. So here, the sixth step. Don't forget to do this. Don't forget to install all the necessary libraries. So basically, we would need these 1, 2, 3, 5, 7 of them. If you have some specific troubles installing them, so please contact me via Moodle, so I will help you to overcome these problems. So then, I will be, from time to time, I will be posting some short videos with the tutorials how to work in Python. So I'm not gonna do this live. I mean, so probably it's gonna be more difficult for you to follow me, and we will spend much more time together. So that's why I will be just making some videos. I will post them on YouTube. So on Monday, you will find on the course page a short tutorial, just some beginning of Python, just to explain what's going on, and some very, very simple tasks there. So I will show you how to deal with that, and you will try to repeat after me. So that's going to be a video. So then after this video, you need to complete a short quiz, 5 points till Tuesday midnight. So I will give you that short time just to keep you working. Okay, so just to motivate that you need to watch this video, and then after watching this video, based on the video, you will have really short quiz, something like 5 points, five tasks, no more. It's going to be very small, very simple. If you understand the video, good. If you don't understand the video, it's not bad, because it's bad because you will fail the quiz. Then on Wednesday, you will have an introductory exercise session to Python. So you will do more exercises. You will try calculating something that is familiar to you. So probably the same exercises as you had on the previous one, on the previous session, but with the help of Python tools, and you will see how easy it is to work there. Maybe some other demonstrations. And then from the Wednesday, you will have the first home assignment on the course page. Don't worry, it's going to be simple because now you see that the only two things we have covered, sample arithmetic average and the sample variance. So therefore, it's not going to be that difficult. So also 5 points for this first home assignment. Yeah, and one important thing, if the exercise in the home assignment requires Python, requires some calculation in Python, you will be asked at the end of the home assignment. So you are familiar to this, you know that usually with the home assignment, I ask you to provide your solution. But when you calculate something with your hand, that's one story. Once I ask you to calculate something with the help of Python, you need to attach the code. So please keep in mind that whenever you do not have your code attached to the home assignment, I don't grade those tasks that require Python. So you need to prove that you calculated this with the help of Python, not with the help of the hand, or not with the help of Excel or whatever. You need to prove that you actually coded this. And I will be comparing your codes such that there are no kind of 3-4 people who produce these codes and others who utilize them. So also please don't use the codes from other students. Try doing this yourself. Questions?
Yes, can I ask you about the re-examination?
Sure. Re-examination for statistics.
It's
It's too
yes,
early,
for
I guess.
statistics. It's too early? But about the previous
Probability.
semester.
Probability.
Yes, probability.
But I need to know what is the period of re-examination. There must be some formal, I don't know, period when the administration sets this. No.
Okay, we'll ask administration.
I will ask them. I will ask them, and I will let you know once I know
Thank you.
the clear picture.
Okay. Thank you.
Other questions regarding today's lecture, yesterday's lecture? It's always better to look forward, just, to succeed, not to look back into the past.
Excuse me. I was said that they don't care, then the examination will be проведена. They just don't care.
Okay, so then I will think about the dates and time. I need to look at your schedule as well, just not to coincide the re-examination with your classes. Okay, I will let you know in the next week.
Okay, thank you.
Other questions?
No questions.
No? Okay. So then, thanks for your participation today. Have a nice weekend. Don't forget about your home assignment. You will find these slides on the course page, and see you next Thursday.
Goodbye.